There are only a limited number of ways in which organic chemistry professors can ask questions on exams. Let's look at hydrolyses of esters as an example. And specifically, we'll look at acid-catalyzed hydrolysis of esters. So the first thing they will ask for an important process like this is, how do you draw the mechanism? Ester hydrolysis with acids. Protonate on the carbonyl, attack with water, nucleophilic attack, deprotonation, reprotonation, and then push the lone pair in from the OH and form a double bond and push out. Now you really must know that mechanism. That would be the first thing I would want to make clear. Does this student understand the process? In this particular case, acid-catalyzed hydrolysis of esters, the reverse reaction proceeds as well. The whole process is reversible. So if you know the hydrolysis, then you know ester synthesis. Take an acid, protonate on the carbonyl, attack with alcohol, deprotonate, reprotonate, then protonate the OH, which is going to leave, push from the OH group that remains to form a carbonyl, and emit water. Okay, so if the organic professor has established that you know the mechanism forwards and backwards, then the next obvious thing to do is come up with a range of substrates, different substituents, things that might confuse you. Can you do this with that carboxylic acid ester or another one that looks different? How about if the alcohol looks different? Your professor may introduce abbreviations to test if you can remember. For instance, in this case, what an isopropyl is in the hydrolysis of this benzoic acid ester. Can you draw an isopropyl all by yourself? If drawing the isopropyl group is not required in the question, you don't really have to do it. Just duplicate the IPR abbreviation. A professor may then test, do the students understand enough to represent closure of a ring and opening of a ring intramolecularly? So in this lactone hydrolysis, we're going to open the 5-membered ring and form an acid and an alcohol connected by a chain, just one molecule throughout. A professor may throw at you different substituents with branches. Probably doesn't matter. Ignore them, just reproduce the diagram. That one is a case where the acid is a bigger carbon fragment than the alcohol, but can the student recognize ester hydrolysis or ester formation where the alcohol is much bigger than the acid? It sounds simple, but that change can catch out people who haven't rehearsed the mechanism over and over again. Another way organic chemistry professors worry students is by putting chirality in the molecule, things that don't really matter most times. Don't worry about it. If the chirality doesn't racemize, then just copy carefully the stereoisomers that you were given in the alcohol or in the acid component. How about if a professor's really out of order? He or she draws something, a mammoth molecule, very complicated. Well, you have the right to abbreviate it. You could just define a substituent as an R group and then present your mechanism in terms of a generic R group going through acid-catalyzed hydrolysis or acid-catalyzed ester formation. And that way, you don't get confused and you don't make mistakes reproducing such a hairy structure. Professors may ask questions backwards, like, okay, we formed this ester, but what alcohol and acid did we use? It's not that much more difficult than going forwards. Or, we formed this acid, what might we have hydrolyzed? Well, you can choose any alcohol you like, unless the alcohol is specified. So we formed this acid and an alcohol. What ester did we start with in a hydrolysis? I suppose a professor could ask about reactions that lead to polymers, like this one where lactic acid polymerizes to polylactic acid, PLA. Interesting stuff because it's biodegradable. You could make sutras for surgery from this. Students sometimes get confused when esters, for instance, are drawn in a different way. Too many abbreviations. Just reproduce them. If the abbreviations are shown like that, reproduce them. Another way a professor can ask a question is on a very similar mechanism and throw in a bit of spectroscopy. Let's look at this example here. We took this ethyl ester and we stirred it up under acidic conditions in methanol. And we formed a product with a peak at 3.6 ppm. What's that? You might even be given a mass spectrum. So then you add up the molecular mass of the product and you add up the molecular mass of the starting material and you find, oh my goodness, 14 less. We've lost a CH2 group here. The difference between methyl and ethyl is CH2, 14. That gives you a big clue. The OMe of a methyl ester might be at 3.6 parts per million, and exchanging out an O-ethyl for an O-methyl is a loss of 14. What we've done here is acid-catalyzed transesterification. And it's good practice. Just close your eyes and think through the mechanism. Protonation of the ethyl ester on the carbonyl, attack of methanol, proton transfer to the ethoxy group, and then push in from the OH, form a carbonyl, and liberate the ethanol. That's how you would explain it. I hope this helps. Good luck with your studies. Bye-bye.